Good morning, Year 12. In our lesson today, we're going to look at how we can use the compound interest formula to find the number of compounding periods and the interest rate. Our first example is Jim invests $35,000 for 10 years with interest compounding monthly. Calculate the interest rate per annum required for Jim's investment to exceed $50,000 in this time. It's a compound interest situation, so I'm starting with my compound interest formula. Over to the side here, I've recognised that this question is compounding monthly. When I've gone to find my I value, which is my interest rate per compounding period as a decimal, I've realised that it hasn't been given to me, and that's the value that I need to find. So I've just written a little note here that I is going to be the monthly interest rate. N, we know that our investment is happening for 10 years and that it will be compounding 12 times in a year, so our N value is 120. Putting those values into the formula here, A is the future value of the investment or the amount that it's going to grow to, and we're looking for when it's going to grow to $50,000, so that's gone in for A. P is our principal. We know that Jim initially started with $35,000, so that's in for P, and we've put I, which is our unknown, and our N value of 120 into our rule. We are now trying to solve this equation to find our unknown I. In order to do that, the first thing I'm going to do is take this 35,000 and move it to the other side of the equation. The 35,000 is connected to the bracket with a multiplication, so when I move it to the other side, the opposite operation is going to be divide. So I've got 50,000 divided by 35,000. When I do that on my calculator, I'll just show you here. When I do 50,000 divided by 35,000, my calculator gives me this decimal, and once again I don't want to write all of those decimal places out, so I've just pressed my double arrow buttons and my calculator has converted that into a fraction for me. That fraction is the exact value, and so rather than rounding this decimal, I've decided that I'm just going to write the fraction here so that I can keep the exact value. So we've got 10 over 7 is equal to 1 plus I to the power of 120. The next thing we need to do when solving this equation is we need to deal with removing this power of 120. In order to do that, let's just consider some things that we're quite familiar with. If I had x squared equals 16 and I wanted to solve that equation to work out what x is, we know that we would take the square root of 16 and we would get that x equals 4. If I had x cubed equals 8 and I wanted to solve that equation to work out what x is, we know that we would take the cubed root of 8 and that would give us x equals 2. If I had x to the power of 5 equals 243, to find out what x is, we would take the fifth root of 243 and that would give us 3. That concept that we're used to using is going to be needed in order to solve this equation that we have here. So we have this thing in brackets to the power of 120. In order to undo that power of 120, we're going to have to take the 120th root of the number that we have here. Now, in order to do that on our calculator, we know that to take the square root, we just press second x squared, and we can do the square root of a number quite easily. If we wanted to do the cubed root, we'd put the 3 in first, and then we'd choose this option here, second my power key, and we'll see that our calculator changes that now to the cubed root, and we could put the cubed root of 8 there to get our answer. So in our case here, we want to do the 120th root of 10 over 7 using my fraction key to enter 10 over 7. We just do a little check and make sure that the calculator is doing the 120th root and it's not doing 120 times the square root. We can see that it's not doing that because the 120 is small here at the top of my square root sign. When I press enter, once again I'm getting that decimal. Now if you like, you can write that decimal answer here. But I've just decided, I've worked it out on my calculator, but I've just decided to leave the 120th root of 10 over 7 in its exact form. And the last thing I need to do to solve my equation is to move this positive 1 across to make it negative 1. So I've subtracted 1 here. On my calculator now I can also do that minus 1 and I get an answer of 0.0029767, etc. I've taken quite a few decimal places here because I don't want to round until I get down to my final answer. Remember over here that we said I was the monthly interest rate, and we know that I is always as a decimal. So this value here that we've gotten from our equation is as a decimal. It's not as a percent yet. So I'm going to multiply it by 100 to convert it to a percent, and I'm getting 0.29767% per month. When we're asked to find the interest rate, it says here calculate the interest rate per annum. So we need to find the yearly interest rate. In order to do that, if this is our monthly interest rate, we're multiplying it by 12, and now I'm rounding my answer to 2 decimal places, and I get 3.57% per annum. The next question looks at how we can find n, the number of compounding periods. So Ariel borrows $3,000 at 5% per annum compounding quarterly. How long will it take for Ariel's loan balance to exceed $3,600? So our compound interest formula, we're compounding quarterly. Our interest rate was 5% per annum, 0.05 divided by 4 to work out the interest rate per quarter as a decimal. We get 0.0125. N is not given to us in the question because that's what the question is asking us to find. So I've just written here that n is going to be the number of quarters, because remember n is the number of compounding periods. I find this quite important so that when I get to my final answer, I don't think that it's in years, because it's not. It's actually in this question the number of quarters that this loan is happening for. So let's put what we know into our formula. We know that we're looking for a balance of $3,600, and we know that our starting amount was $3,000. We've got 1 plus 0.0125 and to the power of our unknown n. Same process as before. To solve this equation to find n, we're going to move the 3,000 across. When I divide that, I get a nice decimal of 1.2. So I don't have to worry about keeping that fraction like I did in the previous question, and I'm down to 1.2 equals 1.0125 to the power of n. In order to find what that value of n is, because it's in the power, we don't have the skills in this course to be able to work out algebraically what that value is. So what we have been doing so far when we've come across problems where our unknown has been in the power is we've been using trial and error. And that's what we're going to do here, is use trial and error just like we did in Unit 3 to find unknowns that are in the power. Now I'll just make the point here that if you have learnt how to solve equations where unknowns are in the power using your logs and you're comfortable doing that, that's not a technique that we are going to teach in general maths, but if you already know how to do it, then you are more than welcome to use that technique here to solve for n. Okay, using our trial and error, I usually start with 5. That's where I usually start, and then figure out if I need to go higher or lower. I'm then substituting in the value of 5, if that's where my trial is starting, 1.0125 to the power of 5, and I get an answer of 1.064. Remember, the answer I'm looking for is 1.2. So that value there is too low. So for my next trial, I've gone to n equals 10, substituted that value in again, and I'm getting 1.132. Still too low because I'm looking for 1.2. I've gone now to n equals 13 because I was getting closer to 1.2 here, so I didn't really want to go too high. N is 13 and I'm getting 1.175, still a little bit low. N of 14, I'm getting 1.18995. It's just not too far under. And n equals 15, I'm getting 1.205. So that's actually gone a little bit over. My arrow to the side here is telling me that exactly 1.2 is happening somewhere between n equals 14 and n equals 15. Now, that means we need to choose between n equals 14 and n equals 15. And this question said that it wanted our loan balance to exceed the value. That means it wants it to go over the value. If I look at n equals 14, I can see that it's still under what it needs to be. So if I'm looking for the point in time where it has exceeded a certain value, then that's going to be at n equals 15. Now, an important point to note here as well is that when we're talking about compounding situations, it only compounds every quarter. So it compounds at 14 quarters and again at 15 quarters. We don't actually work out the balance of this loan between 14 and 15 compounding periods. So your answer here should always be a whole number. So we are going to choose n equals 15 because that's when it's first going to go over the required amount. So I've said here that that means the time is 15 quarters because I've referred back up here where I defined n as the number of quarters, and we would usually give our answer in years if we're talking about the amount of time that it takes for a loan to exceed a certain balance. So to work out the number of years, I've just divided by quarters by 4 and I get 3.75 years, or we can convert that to 3 years, 9 months. For the people who are wondering how we got 9 months, we've just taken this 0.75 and we've multiplied it by 12 months per year to get our 9 months. That's the end of the work for today. In OneNote you will find the textbook exercises that we'd like you to complete for today. As always, if you could take a photo of that work once you've finished it and put it in your OneNote so that we can check your progress. By the end of our lesson today, it's expected that you would now be able to use our compound interest formula here to find any unknown. So the A, the P, the I, or the N.